talking about low mass and resonant Axion haloscopes. I'm from the Quantum Technologies and Dark Matter Research Labs at the University of Western Australia. You can use Poynting Theorem to calculate the sensitivity of LCR circuits from 0 to megahertz and resonant haloscopes on the order of microwave frequencies. A paper that's published earlier this year, if you're interested. In the low mass, we can look at the Axion mixing with a background field to create a photonic degree of freedom which drives an LCR circuit. So let's first distinguish types of measurements you might take which impact on your calculation in Poynting theorem. Resonance measurements are impedance match measurements, and on resonance the reactive component cancels, you get Q enhancement, and you want an impedance match by setting the coupling to approximately 1, and you absorb energy from the circuit. A reactive measurement use impedance mismatch, where either your coupling circuit is much smaller impedance than what you're measuring, or a much larger impedance to what you're measuring. Let's have a look for if your device is a capacitor. Your capacitor is charging and discharging from the source, and your voltage or current are out of phase. That's why we need impedance mismatch. Reactive power measurements does not absorb energy. So the left could be like coupling to the squid, where you have a much lower impedance and you effectively measure current and magnetic flux. To the right could be a high impedance amplifier, where we effectively measure voltage. Energy oscillates between the source and the capacitor and does not destroy photons. Reactive power does not propagate or dissipate out of the volume. It does not need to be the order of a Compton wavelength in size. It's a sub-wavelength phenomena. So in this regime, we can look at it like generating electricity from dark matter. And what you have is a bunch of microscopic quantum phenomena. You have an emergent classical description in this regime. And we have to remember Poynting theorem. Complex Poynting theorem, your part of the complex Poynting vector is the time average part, and the reactive power is the imaginary part. And we combine Poynting vector with Maxwell's equation that leads to Poynting theorem. So when you sub the Poynting vector back into Maxwell's equations, you can come up with this conservation of energy equation, which looks at your sources, sinks, and what propagates out of the volume and what's stored, and basically balances all those systems. There has been, though, a controversy of which is the right Poynting vector to use when you're in matter. Is it D cross B or E cross H? And this was and the conclusion which both were valid, and it depends on the system. If you're looking at canonical momentum, then Minkowski will give you the right answer. If you're looking at kinetic momentum, Abraham will give you the right. Active dipoles, Hertzian dipole antenna, or electret. And the interesting thing is these are electricity generators, is that the electrostatic field as the quantum wavelength becomes large is the dominant field. And that means there's a tangential electric field as a maximum of the boundary, which is an unusual boundary condition and only occurs when the system is active. It makes this act like a current just flowing up and down a conductor. And where you have a magnetic current boundary source, it creates this active dipole. And the same in the electret. For the Axion haloscope, we go back to Axion modified electrodynamics. We apply background field, get a creator photon which depends on that background field, and we can write this background field similar to auxiliary fields in matter, and there's a constitutive relationship which is given by this term here, which is like a D field, and if we take the curl of that D, we get an effective modification to Faraday's law, like you do in all the electrical systems that generate electricity. The Axion with grad A equals to 0, mixing with the magnetic field, and generate a photonic degree of freedom. There is a surface always defined due to how we create this magnetic field, and that's defined by the current. Axion wavelength is much greater in the experiment. We must take into account this solenoidal description of the magnetic field, and there's this effective polarization because we generate effective magnetic current along this boundary, which creates this polarization, similar to how you generate electricity in an electret or active dipole antenna. So it's like an electric polarization with a non-zero curl. There's an extra surface term in the solution to the equation of motion. The surface cannot go to infinity due to the solenoidal nature of the DC magnetic field. Assuming the total derivative is zero also assumes all surfaces go to infinity. Polarization generated by the axion induced fictitious magnetic current boundary is similar to an electric voltage source. The axion modified Abraham Poynting theorem is consistent with the total derivative being zero, and it ignores the fact that the curl of this is non-zero. To be true, it's well known that all surface terms must go to zero as the Compton wavelength approaches infinity. The Minkowski-Poynting theorem identifies surface terms that do not equal zero, and this is a fictitious magnetic current boundary term, similar to an electrode or a voltage source. It's really a macroscopic emergent description of the fusing reaction proton anomaly, which microscopically is a quantum effect. Should we use Abraham and Minkowski, it should be determined experimentally, but analogies with ED suggest Minkowski might be correct. So axion of electrodynamics in the harmonic phasor form in an AC background field, we can write down generally, and we have a modified Ampere's law, and we have two choices of Faraday's law, one that creates the Abraham Poynting vector, and one that creates the Minkowski. We can show using Poynting theorem. The real part of the Poynting theorem is equal to this. Imaginary Poynting theorem is equal to this. And that will equal zero on resonance. And this one gives you two terms. One is the power dissipation, and one is the axion power input, which is your effective source. If we assume there's no leakage out of the voltage, these are just equal to each other. And from this, we show in the paper, this gives you no power output for a Sakivi Haloscope. We can do the same for the Minkowski Poynting vector. We've got the real part and the reactive part, and the reactive part we can confirm equals zero on resonance, and we get a similar formula, a little bit different, but when we look at it, it's exactly the same, and we get the same solution. Now, for a capacitor under DC magnetic field in the quasi-static limit, in this case, it's a reactive measurement. So to first off, the real part of the Poynting theorem is zero, and the reactive part of the Poynting theorem is not. And there's a difference between Minkowski in green and the Abraham in red. The capacitor joined by a wire, we can calculate the B field inside the capacitor and out, but inside the wire and out. In first order would be more fringing fields. We know what the electric field of the capacitor is, and we know what the B field is. We know what the ratio of the two are, and the magnetic field is suppressed compared to the electric field. Modified Abraham Poynting vector and sensitivity assuming the modified Minkowski Poynting vector, we can compare the two. We can look at the imaginary terms, the voltage when we do this calculation, which of course is suppressed by the Compton wavelength. But if we look at the Minkowski version, there is no suppression. So we did this experiment a while ago for BEAST. The Abraham and Minkowski results are here. We can also calculate the current with capacitor. And we put limits, and these limits are consistent with the Minkowski being the right Poynting vector. We used a squid for these measurements. That's how we got these results. We could also use a high impedance amplifier to measure voltage, and this is actually a more sensitive measurement, and that's something we plan to do in the future. We also have this upload experiment, which looks at two nodes. We have both up conversion and down conversion, TN020 and TN011 nodes, tuning close to each other and do a low mass experiment. So we use up conversion. So Jumo power technique, we can apply complex Poynting theorem and get a similar equations to before, but now it's not a DC magnetic field, it's an AC magnetic field. We get the dissipation and the signal that must be equal for a closed system. So now we have this, but there's nothing coming out because it's all kept within the resonator. We need to use the complex electric field, and when we substitute all that in, we get our equations, and we can calculate power. We get this result here. And if we want to measure an axion, which is realized, we get this equation for the signal to noise ratio. And this is consistent, which has been done before, and tells you the power would be emitted in your readout mode if you have a background field that's oscillating. Now we can do a frequency shift technique, is perturbation theory, to calculate frequency shifts, and we get a similar equation to what we had derived before using another technique. We can do it with Minkowski as well, and we get exactly the same. And this is because it's a resonant technique. You don't get that reactive enhancement. And when we calculate the signal to noise ratio, it's exactly the same form as the power measurement, where the noise temperature is random noise in your system. So both are equivalent, give you exactly the same form. Which is better, power or frequency? That's going to depend on experiment. With effective noise temperature, the readout depends on what can be measured with better precision. And we have the same result if you're using Casper or Abraham or Poynting. We have not looked at perturbations of cavity boundaries. That could give you extra sensitivity. We actually, in our lab, we make the world's lowest noise oscillators, and I've been doing this work with Eugene Ivanov for a long time. He's an expert at building these and measure both very low phase noise and very low amplitude. Here's a paper where we looked at Lorentz invariance, and we can look at SY, the type of SY, or fractional frequency fluctuations you can get in this type of system when you're looking for very low frequency modulations. See here is quite good when you look at it as an amplitude of the modulation, parts in 10 to the 14, 10 to 13. And the same with the AM noise. The AM noise gets worse at lower frequencies as well, and is on the order, similar order to this frequency noise. So we really need to do measurements to work out which one would be better. One will be dependent on AM noise, the power technique, and the frequency technique on frequency fluctuation. We have built a second experiment. Our first experiment limits up here. Our next experiments would be just close to the CAST result. And that is the end, because I have not much more time to talk about anything else.